When our force changes, because we've talked about a constant force and then we multiply by distance to get work, but if our force changes, what we have to do is to graph force, and I do include the cosine there because of course we just want the parallel part, but we graph that on the y-axis and that on the x-axis, and what we do is basically have a graph, and then let's say for instance the F cosine is 1 Newton and displacement is 1 meter, and then every square under the graph would be 1 joule, because we do 1 Newton times 1 meter, and that would be a joule. So all you really do is you just find the area under the curve. You add up the squares under the graph, and that's the total joules of work. So it's actually really simple, don't overthink it. So as an example here, we would have a graph, and we might draw in little squares. And I'm not doing it very nicely because kind of time is of the essence. But we would draw in the squares. We'd have each one equal to however many newtons of force times the displacement, and we'd add up how many squares we're looking at. And for those of you who've taken Calc BC, you have done integration, and so you can look at the next slide, and there's an example, but I won't spend a lot of time on it. But what you're really just trying to do is find the area under the graph. And so I'm going to give you a lot of triangles and squares and that kind of thing, so you know how to find the area of a triangle or a square. And so that's the work. So like I said, there's an integration if you're interested. That would be an example, but don't worry about it otherwise. Okay, the next thing we want to talk about is power, and that is the rate at which work is done. And I hope this is overlapping each other. I apologize, but power is going to be work over time, and that will be watts. And so our work will be the same. We'll go through and we'll find work. Then we're going to add one more step to it, and that is we're going to divide by the time that it takes to do that work, and that is watts of power. So we're going to do work over time, so we'll have joules per second, okay? The other way you can get it, and I don't think I'll take the time to look into the exploring the units, but you know, I certainly would encourage you to. But if you go force times velocity, you still are going to get it, because what is a Newton times a meter? Well, that's joules. So you can use both equations. You'll find that they're both on your formula sheet. So kind of keep that in mind. Watch those units. And also keep in mind that 1 horsepower, I think that's what we're kind of used to, is equal to 746 watts. So in your homework, if it asks you to convert back and forth, that's how you would do that. Something interesting about electricity and power, which you can learn about in AP Physics. Okay, so some examples of power. If I run up the stairs slow or fast, I'm going to do the same amount of work. But if I go slower, okay, that's going to be less power than if I go fast. So as an example, I mean, we don't have an engine twice as powerful as another necessarily doing twice the work or going twice as fast, but it will do the same amount of work in half the time. So let's just give an example here. A liter of gasoline can do a certain amount of work, okay? So that's what's contained in a liter of gasoline. But the power can vary. A car could use that 100 joules in maybe 2 seconds for 50 watts of power, where a jet plane would use that 100 joules in a much shorter time because it has a lot more power. Okay, so you're kind of used to engines being more powerful than other engines. Okay, so let's just do an example here. We're going to find work a couple of different ways, and then we're going to divide it by the time. So I have a 193 kilogram curtain that needs to be raised. So obviously we need to raise that against gravity. So that's the gravitational force. Of course, we're used to now multiplying that by a distance to get work. So that's going to be your work, and that will be in joules. And we want it in 5 seconds. So you kind of can see, you know, for a play, you don't want the curtain to just go flying up super fast and startle the audience. You don't want it to go super, super slow either, because you need to get on with the play. So you choose, hey, I'd like to have this curtain raise up in 5 seconds. So calculating that out, you're going to get 2,837 watts. Okay, now you have some motors to choose from. Notice they're all in kilowatts. So of course there are 1,000 watts in a kilowatt. So that's going to be 2.837 kilowatts. So I guess if I had to choose, I would choose the it's supposed to be a 3.5 kilowatt motor. Okay. All right. Now I don't want to get too involved here, but you do have to think about the fact that I was moving this last example up at a constant speed, but what if I was accelerating upwards? I wanted it to just get faster and faster, and we've done helicopter problems before, and it might be worthwhile going back and taking a look at those. But what we're going to do is add in a change of kinetic energy, and we're kind of used to doing that too. So what we're going to do is look at an example where the kinetic energy is going to change as well as the potential energy, and how much time that takes will be the power. All right, I guess we should throw in one other little thing, and that is friction, of course. What would happen if the engine had to work against friction? We want to be careful here and kind of think what would make sense. We're not going to subtract friction. Now, it's going to end up being a negative force against us, that's true, but we're going to add in to get the total energy and then divide by time. So let's just look at an example, because that's probably going to make more sense than any of this. All right, let's say that we have a 250 kilogram helicopter starting from rest, rising up 12.5 meters constantly until it reaches a speed of 5.0 meters per second. If you take into account that it'll encounter about 2,000 joules of air resistance that will work against the motion, what is the total power that's needed? All right, well, let's take a look at this from a standpoint of non-conservative forces. I can look at it obviously either way, but I don't know what the applied force would be. I'm kind of iffy on that. So let's just go ahead and talk about what would that be. We'd have the work done by non-conservative forces, and that's going to equal the final minus the initial. Okay, now initially it has nothing, it's just sitting there. But what we would like it to do is to get up to 12.5 meters high. We would like it to be going at 5.0 meters per second, and we do have to consider this 2,000 joules of energy. So if I look at work done by the applied force plus work done by the friction force, what that's going to equal is the mass of the helicopter. It's 9.8. I want to get up 12.5 meters high, and I would like it to be going 5 meters per second. That's great. Okay, I do want to consider the fact that there is a negative 2,000 joules here. So what I'm going to do is I'm going to add it over to this side. So I'm going to add 2,000 joules. So I'm running out of room here, so I'm going to erase it a little. Just bring that over and show you the math there. So my work done by the applied force, or what's going to happen power-wise, is going to be this plus 2,000 joules, adding this over here. Okay? Now, if you add that all up, we end up with, oh, I didn't calculate that. Oh, that's nice. Well, let's go ahead. I do have the final answer here. I'm going to take all of this, that's all my whole work, I'm going to divide it by 5 seconds, because that's how much time that we're going to need. And I found that by using a kinematic. If you just use a kinematic of V sub F squared equals V sub naught squared plus 2AX, solve for A, solve for time, that'll be 5 seconds. Obviously, I'm going to give you all that information on the problem. So this would take 5 seconds using a kinematic. All right, so if I take all this work, this plus the 2,000 joules, divided by 5 seconds, what I'm basically going to have here is 67,900 watts of power, okay? And that will be the power that I need. All right, so just to kind of recap, I'm going to take the final kinetic energy plus the final potential energy. I didn't start off with anything, so that's 0. And I'm going to add in friction, because over here that non-conservative force was friction at negative 2,000 joules, so I'm going to add that over here. And then I'm going to divide by the time that it takes, which is 5 seconds. And like I said, I will be more forthcoming with the time. I'm not going to have you do a kinematic. But you realize that if you have that distance, you start at 0 and you want to get to 5, you can easily find the acceleration and the time that it takes. So it'll take 5 seconds. Put that under there. You'll get a power from this applied force that you're going to require from this helicopter of 67,900 watts. Okay, this is a really important one because it is so easy that I want to make sure that you get this. The power and engine supply is 35 megawatts. And if this engine ran at this maximum power for 1.5 hours, how much energy would be expended? And this is where you really want to focus in on units. So 3.5 times 10 to the 7 watts. That's a megawatt, by the way. This is a mega, and there is 1,000,000 watts in a megawatt. Okay, mega means million. So this is how many watts that I have. Now, please remember that what a watt is simply a joule per second. And so if I multiply that by however many seconds that would be, and how many seconds would that be? Well, 1 hour is 3,600 seconds. So we are looking at 5,400 seconds here. So I'm going to multiply by 5,400 seconds. The seconds cancel. I am left with 1.9 times 10 to the 11th joules of work or energy. So just take the watts, change them into joules per second, multiply however many seconds you're talking about, they'll cancel, and you'll get left with joules or energy. And I think that's it.